Can you hear me? Great. Hello, everyone. I will start with some very quick stats, but before I start, I have a quick question. How many of you guys are currently subscribed to Netflix and watching Netflix? Please raise your hand. For the record, almost everybody. I should have asked the other way around who is not a subscriber, but I'm not going to go there. So a couple of quick facts. You know what Netflix is, I assume most of you, since you're using it. It's a video streaming service. It's quite large at that point. We have 137 million subscribers as of the end of Q3 2018. We have service in 190 countries. There are only 4 countries in the world that are excluded from our service, and those are North Korea, Syria, Crimea, and China. First 3 because of US government restrictions, the last one because of Chinese government restrictions, obviously. We also have thousands of devices, not just thousands of individual devices, thousands of device types. I have 7 major categories on the bottom, but our service will have to work with everything from smart TVs through Blu-ray players, game consoles, all the way through tablets and PCs and laptops. Really high-level diagram of how Netflix works. Literally, like you have a device that communicates with control plane, which is hosted in AWS, and eventually after authentication, authorization, selection of the movie that you want to watch, you get a reference and you're pointing to a OpenConnect appliance or a server in our CDN or the data plane, which is the cloud on the right-hand side. So to clarify, there have been plenty of Netflix talks and conferences and white papers. Everything below the squiggly white line in the center of the screen is hosted in AWS. Everything above that line is not. So that most of the talk today is about the stuff that happens above the white line. We also have things that are happening in AWS, so they're interrelated, and you'll see how it goes. So to clarify, everything before streaming starts usually called the control plane, AWS. Everything that actually is the actual streaming coming from our servers is from OpenConnect CDN. With that said, let's do some refreshment. What is a content delivery network? Very, very simplified definition. It's a geographically distributed set of content servers attached to networks, plus a way of routing requests to the closest and or best performing server network part. Closest is not the best performant always, like there are exceptions. And with that, let me introduce you to the OpenConnect CDN, a Netflix original. Why is it Netflix original? It is purposely built for Netflix case. It's globally distributed. We have sites and POPs in thousands of locations. We connect directly to residential ISP networks. More than 95% of our traffic is directly connected. It's built on top of highly optimized commodity hardware. Like there are 2, like literally screenshots of 2 of the server models that we currently use. The red one on the left, it's a hybrid model, where you have spinning disk and SSDs in the server itself. The one on the right is more optimized for high traffic applications, it's SSD only. I said we also have purposely built OpenConnect backbone. It's used for exchange communication for control plane and servers that we host. We are available in hundreds and hundreds of locations where we peer with different ISP partners. Those are the public internet exchange points. I have a list on the right. It's just a screenshot. You can see there is a squiggly line in the middle. That's just portion of the list. It's in alphabetical order, so I have to cut the half of it, so you can more than half of it, so you can see any letters. What you will see in any one of those locations will be something similar to the screenshot on the right. That's actual picture of a location where we peer with multiple ISPs. We have 2 stacks of servers, redundant network, different types of servers, and literally like this is the actual physical presence in many of those places. If you want to read more about that, there is the link on the bottom of the page. When we're talking about CDN, we have to talk about the software. The design goals when we were building the CDN were very simple. We wanted to use open source software. We want to have the ability to efficiently read from disk and write to network sockets. We also want to have high performance HTTP/HTTPS delivery. Nowadays, most of the traffic is HTTPS. And the ability to gather information via BGP. With that, the components that we currently are using and we have been using from the beginning of OpenConnect CDN is operating system FreeBSD current, web server Nginx, and the routing intelligent proxy BERT internet routing daemon is used primarily for transferring information from our partners about prefixes and other things that we need in order to be able to do the second part of the CDN, a route request to the most optimal or preferred location. When we talk about software, we also have to talk about performance. Like we not only optimize our hardware, we have finely tuned and optimized our software as well. There is a link on the bottom of the page that one of our colleagues from the OCA development team is talking on about our quest to get up to the point when we are actually capable of delivering about 100 gigabits per second from one rack unit server, very similar to the one that I had on the previous slide. Read it if you are interested. It's a very interesting reading. At that point, I can say that we are comfortably delivering about 90 gigabits per second from a single one-use server on high-performance applications. How does the actual infrastructure look from ISP perspective? In a general case, you have some Netflix sites, some IX site, an IX space for internet exchange, where we're going to have a cluster of Netflix servers. We don't use them individually, they're clustered, where we peer with multiple ISPs via SFI, settlement for interconnect. But there are also servers deployed in ISP sites deep inside ISP network, as close to the users as possible, which makes wins on both sides. From performance perspective and capacity, getting closer to the customer is one of the premises of any CDN. So how does it look like today? Like, this is the network of all the locations where we have deployed servers. The green dots on the screen represent the locations where we have servers embedded into ISP partner networks. The larger orange dots actually are the locations where we have Netflix-supported clusters in internet exchange points. As you can see, it's quite distributed, as the CDN should be. And in addition to the building and supporting that large infrastructure of physical servers, we also care about quality of experience. So service reliability and quality of experience. How many of you guys have seen that spinning circle for the last week or month? Wow, way too many that I wanted to see. For the record, less than maybe 10 to 20% of the audience, I will guess. I raised my hand too because I saw it yesterday. I have not seen it for maybe a year, but hotel Wi-Fi is not the best. So we do not want you to see that. And we don't want you to see that thing. Like we try our best to make sure that those two cases are extinct, but they still do exist. We actually want you to see the list of movies that you wanted to watch, being able to select an exciting show, click on play, and actually get great video quality. Talking about video quality, you have those screenshots. I hope you can see a difference between the two. They are literally from the same scene from Daredevil. They are different bit rates, taken pretty much within the same second. They're not down to the same frame, but they're between the same second or so. The one on the left actually was with very, very, very tiny bit rate. The video bit rate for that sample was less than 200 kilobits per second. Using one of the most efficient encodes that we have available today, it's still pretty watchable. Like you'll be totally fine watching that on your cell phone that doesn't have high definition screen if you're on a restricted 3G network. The one on the right is actually more than 2 megabit per second video bit rate. It's high definition. And why do we have that? Main reason is actual throughput. If you measure, and actually I did when I took the screenshots, when you measure the throughput between your client application and Netflix servers using our fast.com application, the throughput on the left-hand side was 400 kilobits per second. The one on the right-hand side was more than 50 megabits per second. So you don't really need to have 50 megabits per second to watch Netflix great. Like we recommend bare minimum 500 kilobits per second for standard definition, 5 megabits for high definition, and 25 megabits if you want to do ultra high definition or 4K. So with those things actually are impacting the quality of experience of our subscribers. We deeply care, and we want to make sure that you get the best applicable experience for your application at your location at that time. So with that quick introduction of our infrastructure and the things that we care about and the things we actually being bothered by, I want to move on to the telemetry portion of the conversation. So the telemetry, the CDN telemetry system that you're using almost daily is built on the top of the Netflix data platform. There are many presentations about the Netflix data platform available online and in blog posts. There is a link on the bottom. I'm not going to go into details, but really quickly, it's a data warehouse with many petabytes of data. A system that can absorb and incorporate and process hundreds of billions of events per day. It is available for use as self-service internally. You hear that self-service thing from me repeatedly throughout the talk. That's very helpful, very helpful for us. It's very cool to be able to use a platform as a service internally. That's pretty cool. So let's jump in. It's a busy diagram. It actually shows the data sources and different layers that we use when we're talking about near real-time telemetry and long-term telemetry. The first thing on the left-hand side is the data sources. As I was describing earlier, those were the two things above the squiggly line in the first slide, the clients and the servers. Starting from the servers, they are talking with the cache control service and log ingestion. There are two main data types that we care about and we collect there. The first one is health, status, routability, and assets. In that case, assets is simply files, like server communicating back with the control plane what files are available on what server, so you can be steered to a server with actually have the movie that you want to watch, not get 404. The second thing that we collect from those servers is more about event type of information. Those are stats, logs, and events. And events may be something that happened, and maybe something bad happened with the hardware. We are also collecting the ongoing service logs, like Nginx logs, which are sent more in like batch type of processing, but still within minutes. It's not days or hours. On the bottom portion of the ingestion and transformation layer, we have the client telemetry. The thing that happens there is all of the clients that we work with actually are sending telemetry information about the events that happened with the client. Hey, I just started playback. This is the type of quality that I'm currently getting. Or I failed to start playback and this is the error that I got. Those are the main types of information that the clients will be sending to our telemetry system. So with those two, there are a lot of more moving parts and there are a lot of more components inside those two high-level block diagrams, but eventually the data is being enriched and it's being processed and is being actually sent to two main data locations. Like one of them is Amazon S3, the other one is Elasticsearch. I purposely color-coded those two arrows with red and blue color, and you see the server-related events are red, the client-related events are in blue. And eventually, after that, when we start to query those events and use those events, I merged them in purple, primarily to show that at that point, we are correlating the data between these two data sources. They may be directly related with the same tables, same queries. They may be part of it, or they may be just queried sequentially at different times. S3 is the source of truth. This is our main data hub for storage for all of the big data related things. This is where all of the big logs go, and they can be stored there for long term. Months, weeks, years, forever, if you need it. In Elasticsearch, we have mostly event type of data that is shorter duration, more verbose, but for practical reasons cannot be held there forever for a very, very long time. And for the very same reason, we cannot send everything to Elasticsearch. So it's more of a filter type of data, and I'll touch on it later. When we go to the processing engines, we will have Hive, Spark, and Presto on the right-hand side, as well as the Atlas query layer. I'm going to speak about Atlas in a second. Hive is all that big data is actually stored in S3. We do use Hive Metastore. We have been using historically Hive for any type of background processing and transformations. We are moving towards Spark processing at that point. And Presto is available there mostly for interactive queries, things that you are doing like data exploration, something that you want to run really, really quick and you want to get the results fast right away. It's very, very fast, very scalable. It's primarily designed to be that way, and for that reason we wanted to keep it for interactive queries, not for background processing. And the last thing on the right-hand side is the UI and API layer, or you can call it the visualization layer. Big Data API and Big Data Portal are two things available internally, a self-service built by our Big Data team and our Insight engineering team. We do have the Atlas UI, which is talking with the Atlas query, and Lumen is a visualization technology that we're using internally. I'm going to touch on it in a couple of seconds. And, of course, Kibana for visualization for the data that is being stored in Elasticsearch. So let's talk about Atlas really quick. It's multidimensional, near real-time. Latency is literally like in range of a couple of minutes. Self-service again. It is engineered for performance and scale. We do have in-memory storage, which allows really, really fast queries on a large scale. But the data is stored in S3, so it's durable and it's scalable. Like we can scale a lot. We do have UIs for browsing the data and constructing queries, like you have a UI where you can actually filter and create the chart that you want to see in minutes, literally maybe seconds. And we do have dashboards, in other words. There are already plenty of presentations about the inner workings of Atlas and how does it work. Some components of it are already open source. The two links on the bottom are a good start if you want to get deeper there. So let's take a look at how Atlas relates to CDN-related data. We are collecting and sending data on all those servers, literally like hundreds and hundreds of different types of counters. What do you do on usual CDN thing? CDN infrastructure. You want to know how many megabits or gigabits per second or terabits per second you're pushing. So the first thing is your network utilization. But you also are running a server. You care about our server-specific counters, maybe memory utilization, CPU utilization, disk IOPS, requests per second on the application layer, HTTP status codes, bytes per protocol type, IPv4, IPv6, HTTP versus HTTPS. But we also have the luck and the burden to live in a physical world, not in the virtual world. So we cannot just spin up a new server when you need it. We need to deploy a real server, and we care about physical environment too. The thing that I'm showing on the bottom is a screenshot of the case when a specific server actually exceeded the system temperature. I don't know if you can see the numbers, but this is the system temperature in centigrade. And usually it's about 20 to 25 degrees centigrade, maybe up to 30. And AC failure in particular partner site actually drove it up to the yellow zone when it was in the warning, and to the red when it was in complete failure mode. And it eventually was restored. It's AC failure. But those things happen. Like when you're talking about thousands of locations, thousands of partners, things like that will happen all the time. The thing that we do is we have that information available via API, UI. We get an alerts, and in some cases it's non-actionable. Some cases it's actually quite actionable. Like we may need to reach out to that partner and say, hey, what's going on with your AC? Go ahead and fix it, because there are cases when things like that are in unmanned sites. There are literally like no humans at the place where the servers are, so they need to send somebody there and actually take care of the air conditioning if it's broken, if they didn't know about it. In some cases, you may get back, oh yeah, we know about it. It's already taken care of. Women. Women is there is a link again on the bottom of the slide. Women is a dashboard technology that was developed internally in Netflix. It allows internal teams to create dashboards literally in minutes. It's very, very, very helpful, very useful for when you're trying to aggregate data on different layers. It's about variables, filtering. It's very, very handy. It has different visualization layers. I'll have a sample coming in a second or so. So to summarize it, for the longer-term multidimensional data, for near real-time data that we have like in Atlas, it's multidimensional. Like you also want to know what is the current throughput per cluster or server. We want to know what the operating system of the server was. Literally like when we are upgrading the firmware of those OCAs, we have different versions. For obvious reason, like we may want to do canary analysis, or maybe have some issues that are related to a specific version or hardware type. So all those things are different dimensions, but the storage is limited. Like S3 is quite scalable, but scaling costs money and impacts performance. So we have to limit our verbosity, our cardinality at that point. That's the multidimensionality. The other thing is the event-like data that we have in Elasticsearch in Kibana. Those are mostly messages, event data with high level of verbosity available for search and visualization. Again, limited time frame for practical reasons. The big data, the S3 thing that's being backed up being queried by Hive, Spark, and Presto. This is large quantities of very verbose data coming for both server and cloud logs. We have longer-term storage. We keep it for a long time. It's needed to be there mostly for hour after or day after processing, things when you have to aggregate and join data from various sources, for example. So the main data hub in source of truth in S3 plus Hive Metastore. Big data transformation are done via asynchronous jobs in Hive and Spark lately, Presto for interactive queries, and the visualization layer is Tableau. Tableau is mainly used for either interactive queries, data exploration, scheduled reports, things that you want to do on specific cadence, and it's using mostly based on data extracts, not directly connected. Let's take a look on some example next. It's a real-world example from a relatively small partner site. I called it "What happened to my traffic?" So the thing that happens is it's literally like escalation at that point. Traffic is not being served from the most optimal location as we want it to be. Servers are perfectly healthy. Connectivity in general is really good. Configuration and route advertisements are also okay. Quick moment on the Lumen dashboard, which shows the total number of concurrent connections for that particular site. Site in that case is a location, like number of servers at the same place, same location that are working together. Shows that the top chart in light blue shows the total number of TCP connections in established state. The bottom chart in red actually shows the total number of TCP connections in seen receive state. So all those are connections in half open state. So what does it mean? It means that the client was able to send the initial part of the TCP three-way handshake to the server. Server responded back, but the three-way handshake never completed. And clearly, it was a typical example of a broken return path. So the network problem here was not that the client packets weren't able to get to the servers. It was the other way around. The response from the servers wasn't able to get to the packets. Like literally, like with that level of information near real time, you can quickly take a look and say, oh yeah, your return path is broken, and quick TCP trace route or just simple trace route will confirm it, and it's very easy to identify the issue there and get it fixed. SiteMove, another example of real-world problem that we solved using the technologies that I was describing earlier. We had an earlier case of site migration. Site migration in that case is moving physically the traffic for a particular region from a subset of servers in the same location to a new subset of servers. So all the peering and traffic for multiple partners will have to be migrated from the old location to new location. But during the migration, as part of the validation, we identified some noticeable degradation in performance. Still not noticeable by customers, but noticeable by us, something that we really want to get fixed. Like we want you to have the best optimal experience that you can. So we started to take a closer look on it. So something's wrong, somewhere it's not right, but where exactly? That's a typical thing that we start with. Yeah, something's broken, but where? Is it the servers? Nope, they look fine. Is it increase in retransmits? Nope, they also look fine. Maybe it's physical connectivity or bad optics, patch cables, and yeah, maybe. Like it's always a suspect when you have a physical move, but it wasn't likely because we didn't see increased interface error. So it's one of those things that you get to the phase of head scratching and thinking, okay, what's going on here? Maybe something else. How about latency? So quick Presto query, literally like it takes 20 seconds to type that Presto query and another 30 to 50 seconds to run it, actually gives me the date integer, the hour, the site name, and the quiet ASN, literally like just that specific ASN for that specific set of ISPs or subset of ISPs, where they're part of the workflows. And the thing that we're calculating is the median TCP round trip latency in milliseconds, as well as we are counting the total number of sessions. So literally like obviously I replaced the table names and DB names, but it's simple as that. Literally like that's a screenshot from the internal big data UI that you can type something like that, run it, and you get information right away. And the result after that can be exported either as a Tableau data extract or a CSV file and visualized in Tableau itself. The top chart is showing the round trip latency between the old site and the new site. The old site in green, the new site in orange. You can clearly see like the jump there. Like it's not what you want to see in cases like that. The green and the orange on the bottom is the total number of sessions over time. So yeah, something was broken, and the broken thing was there was missing configuration on the partner side, specifically on the BGP layer, in such a way that packets from the servers have been sent directly over the direct peering in the new location. But the packets from the clients to the servers were going the scenic route. They're actually going across the ocean through transit to us. But those are packets from clients to servers, so they're very, very small. So you wouldn't see it, like if you look just on network levels. But when you look on the latency like that, it's like, oh yeah, it's right there. Like, yeah, something that needs to be fixed really quickly. So another example of Tableau plus big data is, I mentioned earlier, is aggregation of data over a long period of time. The thing that we are showing here is a dashboard, a screenshot of a dashboard, a report created based on daily streaming data. This is the total data for all of the files that were delivered by all the servers on the CDN on a particular day. Each of the vertical bars is a single day, and the color coding is a different encodes. So the thing that we have here is a rollout of a new, more efficient encode for a specific device category over time. This is the typical example of when you aggregate the data from the servers. So we have the Nginx logs, compare and correlate and join against the actual data about the files that are being downloaded and additional information about their encoding type will give us the capability to see how the rollout is going. It's something that you don't have a real-time dashboard for, but when you look on it in an aggregated way like that, you can see, yeah, we are doing well, like we are on target, like we are getting where we want it to be with that particular rollout. Okay, another example, and I'm calling it a fictional screenplay based on past events. It's fictional screenplay because it's not a real screenplay, I made it up. So fade in, you're on call. By the way, how many people are on call right now? Please raise your hand. Nobody? Oh, one. Okay, so you don't have to imagine. Everyone else, you can imagine that you're on call. So your customer support team is pinging you about increased volume of calls from customers of XYZ ISP with specific category of devices that are intermittently failing to start playback with error code 1234. So are you aware of any current issues that could cause this? EU. Not really, but let me take a look. Yeah, so everything looks green on my side. It's going to be something outside of our network. Maybe we can get some more details, sample client IPs, HTTP, or maybe Wireshark captures. I have been surprised by our tier 3 customer support team. They have been capable to get Wireshark capture or HTTP capture from impacted customers in hours. I've been impressed by that, but it still take hours. Like in the meantime, like you have to do something about it. You don't want to stay. Maybe you can try something in parallel. Maybe you can go to stage 2 of the investigation. Stage 2, option 1. Use your psychic abilities to identify and locate the impacted customers. 2, run or fly, your choice, really, really fast. Ring the doorbell, introduce yourself, use your smartphone, smartwatch, phone, tablet, laptop to take the captures, analyze the captures, correlate the data, identify the issue, mitigate the issue, fix the problem. 5A, optional. Only if the problem is a fiber cut, you can use your laser vision to quickly splice the damaged fiber cables. Yeah, not really. Like only if you have such superpowers. If anyone has them and is looking for employment, ping me after the presentation. We will find something for you. Anyway, you have to wait, or maybe not. Maybe you can try something else. You launch a new real-time query on top of Mantis streaming processing platform that we have internally. This is like the thing that belongs in the ingestion transformation box that I had on the left. Literally, it's a SQL-like query. It's not pure SQL. A SQL-like query say select star from stream where device equals 1111 and ASN equals 2222 and error code equals 3333. Couple of minutes later, you have the first verbose data in the UI and Elasticsearch. 5 minutes later, literally, we have enough data points to be able to correlate the problem and see the issue. Bad connectivity between specific ranges and specific specific set of servers. And then 4, you can mitigate the issue. Reroute traffic in scope away from the impacted servers. So great, we fixed the problem. But wait, is that really great? Do you want to be in that situation? Is that really good? Well, let's take a look on some numbers. So time to detect unknown, maybe a couple of hours. It depends when the users called customer support and when they went through the chain of escalation up to level 2 tier 3 and they actually called you after that. So not really good like that, that's bad. Time to recover 10 to 12 minutes, that's kind of good if you are in the point when you're actually capable of using the real-time streaming platform to get the data that you need. If you had to wait for the customer support team to get the captures for you, maybe a couple of hours, which will be really bad. So for us, the lesson learned there was we clearly need to work on improving the resiliency of that data flow. And we are working on that, there's no question there. In parallel, for the next time that something like that happens, for us, the lesson was there, we can improve. We can already have a job that's running all the time and collects that data for such issues and stores it in Elasticsearch. Then maybe we can have a Kibana dashboard that visualizes that data and allows us to be able to interact with it. In addition, we can also implement an Atlas metric and maybe a trigger an alert based on that metric when it exceeds specific threshold, and also implement auto mitigation on top of all those things. So we did it. Yeah, we have all those things. We actually have a metric that captures all those specific events with a specific signature going to Atlas and a threshold alert. The screenshot on the left is it's a sample of the alert that was triggered at some point of time when we exceeded the threshold. I don't know if you can see the steps, but it's literally like a step level function, and each one of those is 1 minute. So time to detect at that point is down to between 2 and 3 minutes, which is pretty close to real time as you can get. Time to recover, 5 to 6 minutes. We already have the information. It literally takes like just a couple of minutes to figure out where the problem is and implement something. And I have an asterisk that says when is actionable a service side. There will be cases that there will be nothing that we can do on the service side to mitigate the issue. That will be a case when ISP connectivity has significant issues to connect to the internet in general. The screenshot on the right-hand side is a screenshot from a minor outage, specific ISP in the Northeast United States when multiple circuits were impacted at the same time. So at that time, literally, like you see that there was impact for up to an hour, but there was nothing that I can do on our side to mitigate it. Takeaways. So near real-time collection and aggregation of data for all applicable layers is really fundamental for you being able to have the complete end-to-end picture of your requirement. Capability to correlate events from all those sources is very helpful to really get the holistic view of your service. We are actually capable of identifying via specific identifiers, which is nothing, just an identifier. What was the instance? What was the server in AWS that created a specific type of data manifest that was sent to the client? What was the content of that specific piece of data that was sent to the client? Then what client talked with what actual CDN server, and what was the server response, what was the client response? So all those things, when you piece them together, they tell a completely different picture. Like it's very, very, very helpful to really get the picture. You cannot guess at that time, you know it. Using a real-time data processing will help minimize TTD and TTR. Well, that's obvious, but if you need justification, especially if downtime means dollars, you can show an improvement in TTD and TTR, you probably will get justification for getting the dollars to invest in a such system. Longer-term trends can help you with longer-term things over time. See the boiling frog fable if you haven't heard of it. This is a fable when a frog gets dropped in the boiling water and he probably would jump out and save his life, but if the frog is being put in tepid water and temperature is slowly risen to a boiling point, he may get cooked alive. You don't want to be in that state. Like, you want to see that thing coming even before it happens. Also, if you have some of those technologies available but you're not using them for SRE needs, go ahead and start using them. They can help a lot. And I realize you may not have those capabilities today, but you may get it in the future. Cloud vendor of your choice can help you get things done. And I think I'm out of time at that point for questions.
If you have any questions for Ivan, we can answer them afterwards. We're going to get on to the next talk. But thanks so much, Ivan.
Thank you, everyone.